Okay, so at the start of the season, we had a few goals. One of them being to be able to grab the box in all orientations. So what we did was we looked back to a couple of robots. One of the main robots being 1/18's tote robot in 2015, which is why we use these wheels on bungees, because it really seemed to be effective. So essentially what it does is as it sucks up the robot, the bungees spread out, allowing it to suck up at most angles. One of the problems we did come into is we didn't really have enough time to work out the strength of the bungees we needed, and the hinges we have on there have a little bit too much slack in them, so it doesn't quite keep high and tight. When we first started out, we gave the motors a little bit more room to fold in, and later on we realized that let the hinges hang down and get in the way. So we kind of shortened that gap up to kind of clean it up without having to completely redo our design. But what this allows us to do, picks up any orientation except for the 11-inch orientation. But what we found is that even in the 11-inch orientation, you can roll around it and pick it up, because there is a 13-inch orientation in the 11-inch orientation. This mechanism also holds our hook for the climbing system, which we'll talk about later.
For the drivetrain this year, we chose a standard tank 6-wheel drive with traction wheels. This is simple and cheap, easy to build fast. We didn't see any reason to strafe side to side, as this doesn't really lend itself to this game. Our arm mechanism this year has 2 degrees of freedom. The main reason for the second degree right here is in order to keep the intake mechanism inside the 16-inch limit of the frame perimeter as it goes up to its full extension. It serves a dual purpose as well, in order to hold the power cube inside the intake as it goes up to its full extension. Powering this mechanism is a AndyMark Redline 775 motor with a 75:1 gear ratio versaplanetary gearbox with another 2.66:1 gear reduction to the wrist for a total of 200:1 gear ratio on the mechanism.
Alright, so one of the main features of our robot is this arm mechanism that can raise up to about 7 feet or lower all the way down to the ground to pick up the power cubes off of the ground. So I'm going to talk a little bit about that. Some numbers. This axle is about 46.5 inches off the ground. Our arm end to end is about 48 inches. The axle is about 1 inch in on either side. So as far as creating a moment arm, you can imagine there's quite a bit of torque out over here. Where there's about 20 pounds of mechanism out here, and accounting for the arms also. So at a worst case scenario, when the angles are disadvantageous for the actuators here, it comes out to about 270 pounds of force pushing downward. We originally thought we might be able to get by with 1 dart actuator to hoist this whole thing up and down, but being able to only provide about 204 pounds of force each, we quickly realized after doing some math, we would definitely need 2 dart actuators to manage this. So, a couple other dimensions for you. At the farthest out point, we'll talk about the perimeter rule a little later. You can see this is folded in at the moment, we'll get to that in a second. But we wanted our mechanism to be able to support the worst case scenario. So, like I said, this is about a 48-inch rod, but even beyond that, if this is folded out, that adds another 11 inches beyond that, with a lot of the weight being right out at the end. So, again, this worst case scenario is about 270 pounds on these darts, and together they could produce over 400 pounds back up toward to support the rod. So it was perfectly sufficient. Something else of note is that this axis, or this point where the vector is coming back up, is about 5.5 inches from the point of rotation. a way this design could be optimized with a little more time and energy is if this axle was pushed farther down the arm to be at a more advantageous ratio. The reason that it was this far down is because we only have 12 inches of stroke to work with. And so to be able to angle all the way from the ground up to about 7 feet, we needed to have it this far back to work with the stroke we have. And in the CAD model, I was designing the CAD, we didn't have a completely well-defined model for how high this is, so I modeled it on the conservative end. So it actually ends up, when we built it in real life, that we actually were able to go a little higher than we had anticipated from the CAD model, which is great. And we were well within the bounds of the darts, so they work great. If you're interested, go back and check out the day 2 update video I've posted. There's a CAD model with some dimensions on there you might be interested in, and a good discussion in the comments about kind of the geometry of this.
Control system on this robot has to be very precise. We built it with very tight tolerances to be able to stay within the frame perimeter at all times and be able to accurately sense where this arm is at any given time. So to do that, we have these 2 dart actuators, which both have a potentiometer that allows us to get absolute positioning on their movement. Now that just gives us, of course, the rotation relative to that. It's very well documented. You can look it up and translate it eventually into inches movement here. From there, you can take some basic trig and work out the rest, but you need to make sure that those are accurately tuned. And even when we go to regulate these to go up together, we are running the PID control straight on the talons, and we're doing it in units of the potentiometer's rotations. And tuning each one independently, without them connected of course, and accounting for slightly more resistance in one than the other. This is very important so that when you put it together, it's very tightly together as you change the position. Now we even have, to help us and make sure that math was right, an encoder on this axis here, so that we can see the angular change and verify that everything worked clear as kind of a backup in case any of our measurements was a little bit off. Now on the wrist here, we ended up going with an encoder and a limit switch. So an encoder here just sort of counts the difference, and then we use a limit switch to hard align where it's at. Now while this works and provide accurate sensing, we would much prefer the potentiometer had we had the stuff on hand and more time to mount it properly. Because you can run into issues where, depending on where you start or whatever, it has to go into a calibrate sequence over time, unlike the potentiometers on the darts. And that covers the control system for the robot.
Okay, so I'm going to talk about one of the aspects that has received lots of questions in our day 2 video. If you look at go back and watch our day 2 video, in the comments section, there was a person who was asking about how we stay within the perimeter rule, the 16 inches from the perimeter of the chassis. And the way that we do this is by bending this wrist up so that the entire length here is within that perimeter rule. Now, to do this, you can imagine as the arm actuates up and down, we're going to go through a range of angles where this will most definitely be breaking, if we had it extended, that it would most definitely be breaking that rule. So what we've done in the software is through the geometry of the entire mechanism, we can calculate explicitly a lower angle and an upper angle, and in between that is where we would be breaking that perimeter if this was extended. So what we do is when we are below the lower critical angle and we are approaching the lower critical angle, we have the software automated to twist the wrist up automated, so that then we can traverse through the dead zone to where we reach the upper above the upper angle, and we can then redeploy the wrist automated, and all of the equations were solved so that happens all the time. We are all the time live calculating the solution of the tip of our end effector
And if the end effector is going to break that perimeter, the wrist automatically folds up. And so we can then traverse through our dead zone without breaking the perimeter fold.
All right, so the last mechanism we want to talk about on our robot is the winch, to climb up the tower and get the points of thing. So the way this works is we have a hook up here. We made this we kind of made a composite of our own. There's aluminum with some plywood in the middle and more aluminum, and it's all bolted together. The reason we did that is simply to have some thickness, so it's easy to mount. The hook is about 4 inches in diameter, and so to catch a 1 1/4 inch rung or a 2 inch bar over the side, it should be big enough to catch either. You can see we've got steel cable running through these small cable management guides. You can also see, I don't know if you can see this, but these open to the top. So the idea is when we line up with the rung, raise the hook up underneath, it will back up. As soon as this catches, the whole arm will lower. We'll have to turn to the right, start rotating. It'll lower, and as it lowers, the weight of the robot and the force of the arm pushing down will make these cables pop out of the guides, because this is a pretty flexible plastic. We'll have to rotate, and then you can follow the cable down, and down here we have a steel eye bolt, and the cable goes into a spool down here in the middle. Now the spool has a big sprocket on it and a chain, which is powered by an Andy Mark Redline motor. The gearbox on it is the same as our wrist action up here. It's a 25-to-1 with a 3-to-1 on top of it. And then from that, we gear 2-to-1 with the sprockets. And so we have a total gear ratio of 150-to-1 with a 2.5-inch pulley or spool for the cable to right up. So according to calculations, this should have the ability to pull about 600 pounds of force on this cable. The robot only weighs about 110 pounds, so we should be well within that. Now, disclaimer, we haven't tested this. We don't know if it's going to work or not. We kind of ran out of time and didn't get a chance to test it. So, we're going to test it right now. Right, back up. That's clear. The motor's clear. You back straight up. All right, lower it. There you go. Lower the arm. And then rotate to the right. Keep going. Keep going. Rotate. It's working. Rotate. Give it the beans. All right, you gotta give it the beans, man.
Retract it a bit?
Yeah, I would retract some more so the center drive is lower. And because yeah, we can. All right, now you got a spool, and I would lower this all the way down. That's backwards. Switch. That was backwards. Go the other way. It's going. It's going. Yeah, I told you. He thought it was going to be fast. I'm like, I don't believe it. Well, still on the spool. That works. Keep on moving. It should get easier as time goes. They're on 20. Well, let's speed it up. Is it 20% throttle? Why is it on 20% throttle?
It's going till we're a foot off the ground.
Keep her moving! I just don't want to snap. That would be a bad day. Yeah. That would be a beautiful All right, so I kid you not, that was our first actual test of the hook and winch system, and I think it went great, personally. I think the cable releases worked really well as kind of a passive guide for the cable, like safe throughout a match. Our hook holder and release worked pretty well. Even the winch, as you saw, you know, it was slow, but I actually figured out after the fact that it was pretty underpowered. I think we were only at 20 or 25% power, so we could theoretically speed that up quite a bit. The part that actually failed was that our spool, we're actually using Versa hubs from Vex. They're fiberglass or plastic, and we had several extensions in there to make a big, you know, wide spool. And that's the part that actually failed because there was so much force from the steel cable that it actually sheared through the plastic. And that's when the whole bot fell. So, all in all, I think there's some key takeaways, you know, some concepts here that could be applied and updated and improved upon. And I'd love to see if you guys experimented with a hook and a grapple or a winch like this. I'm fascinated to see what you guys come up with this build season. Hopefully you found some of this bot inspiring or funny or interesting. And I'm excited to see what you guys come up with. So good luck on your builds, and I'll see you guys at the competition.